So this is a continuation of chapter 6. We're now going to get into what we call quantum theory, or how we believe, or to kind of point out what the emission spectra kind of told us about the atom. So again, highlighter might be helpful. Atoms and molecules can only exist in certain allowed states. So there's what we call a definite amount of energy for these electrons to exist at. So when a gaseous sample is excited by radiation, the sample can absorb only a certain value of energy. So this is why we have the different energy states that we see in the emission spectra. So why does hydrogen have those lines at those certain nanometers? It is because of those energy levels that hydrogen has in its atom. So when a gaseous atom or molecule changes from one energy state to another, okay, we are going to see that the energy is absorbed or emitted is just sufficient enough to allow it to go to the next energy state. So that is why we call it a quanta, or a specific discrete amount of energy for that to take place. So to just give you some background, if you remember your Bohr model, you have your nucleus, and then when Bohr thought that the electrons somehow orbited the nucleus, and when you learn this in middle school and even first year chemistry in high school, we kind of used it as kind of our starting point and our starting model, okay? So Bohr was correct in the fact that these electrons exist in energy levels, okay? But he thought that since they orbited that nucleus, that the distance between these energy levels was exactly the same. So some books put it as it's a ladder. So those energy levels were exactly the same distance apart. But when experiments started to get done, they started to see these emission spectra, and they're like, wait a minute, that doesn't work, because they all should have the same distance between the lines, and so on and so forth. So if we think of an energy level, so this is energy level 1, and this is another energy level higher than that. And we are going to draw an electron as an arrow, and you're going to see that further on in our discussions. So if this is the nucleus, okay, the electrons are always going to be in what we call a lowest energy state. So that is what we call the ground state, lowest energy state. So this electron wants to be in that state, but if I put energy in, so write an arrow, put energy in, and that could be electricity, that could be a flame test kind of situation. So if I excite that electron, it's going to move up to a higher energy state, okay? It's going to move up to a higher energy state. So this is going to be called what we call the excited state. So it's not the ground state. So it is a higher energy state, whatever that happens to be. Well, just like human beings, we can't exist in an excited state for too long. The electron comes back down to its ground state. Well, when that happens, energy has to come out. Okay, so energy comes back out. Well, the energy you put in has to be the same as your energy you got out, conservation of energy. So with that understanding, we then could understand that the distance between these two energy levels is dependent upon the photon that comes out. And Planck figured out that relationship. So is that in the visible range, it is in the IR range, it is in the UV range, whatever range it happens to be. Okay, now when the electron comes back down, that's really what we are observing when we see the emission spectrum, okay, is when the energy goes out. We don't see the energy going in, but we could compute by what light we see when it comes back out. Oh, and one other thing, if the electron is coming from the excited state to the ground state, it's relaxing. So that's a term you might hear used as we go forward. So with this quanta, okay, we're going to do some calculations with it and go a little further into how we can figure out these energy levels. So let's just start with some basic stuff. So find the energy of a photon with a wavelength of 625 nanometers. So the first thing you must do is convert the nanometers to meters. And again, you could use any, you could use 10 to the negative 9th or 10 to the 9th and divide it into it. But usually if it's in the visible range, it's going to be 10 to the negative 7th meter. Okay, if it's between 400 and 700, that's usually going to be what you have. So if I need to find the energy, I'm going to do 2 steps, and then I will show you the 1-step version. So I'm going to take the speed of light and divide the wavelength into it to find my frequency. So I'm going to take 3 times 10 to the 8th meters over seconds and divide it by my 6.25 times 10 to the negative 7th meter. Okay, again, I can't do this with nanometers. So this comes out to be about 4.8 times 10 to the 14th hertz, or inverse seconds, whatever you like to do. And then I got energy is equal to Planck's constant times the frequency. So I'm going to take 6.626 times 10 to the negative 34th joules seconds. And then I'm going to multiply it by my 4.8 times 10 to the 14th inverse seconds. And then my energy is going to be 3.18 times 10 to the negative 19th joule, 10 to the 19th joule. Again, that was a 2-stepper. You can take Planck's constant times the speed of light and divide the wavelength into it. You will get exactly the same answer. Okay, so it's up to you to figure out which way you like to do that better. Okay. All right, so the second problem here, a little bit more involved. That was just more of practice of how to do the calculations. So if the energy required to break the chlorine-chlorine bond and chlorine Cl2, the diatomic, is 242 kilojoules per mole, what is the color of light that has the correct energy to break such a bond? So we will be talking about bonds in a couple more chapters, but I kind of like this one because it kind of introduces energy and stored energy that we just talked about in thermo. So if I had a 1 molecule, okay, so we're talking about 1 molecule and we're trying to break this bond. We're trying to break that bond. So I have kilojoules per mole, so I could convert this into how much kilojoules per molecule, because a mole, that's going to be a lot, and I'm only talking about 1 molecule here, okay? So I'm going to convert this. So 242 kilojoules per mole, and what do I know about every mole? Well, it's 6.022 times 10 to the 23 molecules, okay? And then I could convert this from kilojoules to joules, okay? And just so I could use it in an equation up here. So energy has to be in joules, so that's why I'm doing that last step. All right, so this comes out to be about 4.02 times 10 to the negative 19th joule per molecule, okay? Now, makes sense, that's a pretty small number. We're talking about 1 little molecule here, not moles, okay? So that makes okay sense. So if I want to know the color of light, okay, I need to find essentially its wavelength, okay? So I'm going to use this equation, but I'm going to manipulate it to get to wavelength. So I'm going to switch the position there. So I'm going to have Planck's constant on the speed of light divided by the energy, okay? So wavelength is going to be 6.626, 10 to the negative 34th joules seconds, 3 times 10 to the 8th meters seconds. And then my energy. So this comes out to be 4.94 times 10 to the negative 7th meter. So then you got to convert that back to nanometer again, 10 to the 9th. So you're getting rid of the negative 7th, and then you're moving the decimal 2 over. So you get 494 as your nanometer, and that is in the visible range. Okay, well, what color is it? Well, it actually happens to be green. Okay, I'm not going to ask you that question. I like it because you might recognize chlorine. Sometimes you hear it mentioned green light can disturb that bond. So that's really why I have it mentioned. I'm not going to ask you to do that. But I am going to ask you to find the nanometers and know that it's in the visible range. Okay. All right, so to kind of summarize what we're talking about with this quantum model, when we are talking about anything to do with the quantum model, we are going to focus only on hydrogen, okay? And that's because Hydrogen only has one little electron, okay? And so it is much easier to study than something that has multiple electrons. So we can study its energy levels because we could see how much it absorbs or emits energy. And we could tell what its fixed energy levels happen to be. So it's sometimes called quantized, meaning there's a certain amount of energy that is there. So for hydrogen, okay, this is hydrogen's energy levels. So energy level 1, this is your nucleus down here. You have energy level 1, 2, 3, 4, 5, and so on and so forth. Well, if we had Bohr's model, these energy levels would be equally spaced. So write down not equally spaced. And again, we figured that out because of the emission spectra that we were able to see that the electrons, when they came back down to the ground state, that they emitted different wavelengths of light. So these energy levels, okay, going from energy level 1 to energy level 2, that's a pretty big jump, okay? But then 2 to 3, and then 3 to 4, and then 4 to 5. So the further away you get from the nucleus in hydrogen, these energy levels get closer and closer together. That didn't work with Bohr's model, so that's why they had this understanding of these have to be distinct energy levels for every atom. And these electrons, when they jump up and come back down, we have proof that that is true, okay? So to summarize this, there are what we call series that you find with the light that's coming out. So we have 3 different series. One is called the Lyman series. And what that means is if an electron is at a higher energy state and comes back down to energy state 1, it emits what we call UV light. And UV light is somewhere between 10 and 120 nanometers. Again, I don't want you to focus on the nanometers. I want you to focus on the light that's coming out. So it's called the Lyman series. The one that we like a lot is the Balmer series because this one happens to be in the visible range, okay? So if something is at a higher energy state and the electron is a higher energy state, an excited state, and comes back down to energy level 2, we see it in visible light. And again, I do expect you to know visible light is between 400 and 750. And finally, the last series that we are going to focus on is called the Paschen series. And that is if you have it starting at a higher energy state and it ends up at energy state 3, that is what we call IR light. I do not expect you to know what the nanometers are for that.